screen so I can show the title. So there we go, vectors and geometry. There's 2 exercises involved in this particular OneNote. I'll try and go through both today, but I'll do them in parts. So we're going to start by talking about collinearity, which is the 4F. And this is where things are starting to get a little bit more complex and a little bit harder to visualize. So obviously in Unit 1, we did a lot of vectors, but it was all in 2 dimensions and it's pretty easy to visualize. 3 dimensions a little bit harder, and collinearity is one of those things. So let's just go through the definition first. 3 or possibly more points are said to be collinear if they exist in one straight line. So as you can see there, I've drawn 4 dots and I've shown you a situation where A, C and D are approximately collinear. B is not collinear with any other pair. Obviously B does form a straight line between each individual other dot, but B doesn't form a straight line with 2 other dots in this particular situation, so it's not collinear. Hopefully that, does anyone have any question about that definition? That's collinearity. So just talking about the algebra side of things, I know some people are writing stuff down, so I might just scoot there. In terms of algebra, we're going to revert back to the idea of parallel lines. So if U and V are parallel, then remember we defined that U, vector U, equals some scalar multiplied by vector V. That's our definition of parallel lines, and that's a result of parallel lines. It's in the same direction, it's just a different length. So scalar K changes the length, and we don't know what K is. So that means, if I have a look at my example there, A, B and C on the orange dotted line, if A, B and C are collinear, then that means that AB, vector AB, is equal to some constant times vector AC. So this distance here is some constant times vector AC. And in this example, K is obviously less than 1. But they're in the same direction, so K is positive but less than 1. We could also make the statement that AB is some constant times BC, or that AC is some constant times BC, or whatever the statement is. What's important though is that these 3 points are collinear if 2 vectors created by those 3 points hold the property of parallel lines. And there's 2 reasons why they're collinear. First, they're in the same direction, so that multiplication by K implies that directionally they're the same. But secondly, this definition here shares the point A. So they're 2 vectors that have that common point A, and also they're parallel. Therefore, they must be collinear. You couldn't say it, so you've got to be careful. We couldn't say it if there were 4 points, and the 4 points were here, 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 and here. We couldn't say those 4 points are collinear, even though this line segment is parallel to that line segment. If I call this A, B, C, and D, even though AB is parallel to CD, I can't say they're collinear because they don't share a common point in that parallel line statement. The fact that down here this shares the point A means that they're parallel, they're in the same direction, and they have to be the same line, so they are collinear. Does that make sense? So just be careful. Basically, it always works with 3 points. If you can prove that any vector line segments created by the 3 points are parallel, they're collinear. But if you've got 4 points or more, it might not work. There has to be a shared point as well. So just be careful with that. So I've stolen a bit from the textbook. I've had people say they'd like me to be consistent with the textbook, so I'm trying to do that. So this is straight from the textbook, and it's the idea of proving collinearity. We're going to prove something, but actually what we're going to do is we're going to start with the assumption of collinearity, and then we're going to flip that around to show what things need to be true for collinearity to be true. So what we actually want to show here is that AC equals M times AB, where M is just some constant, it's like our K, but the textbooks used M for some reason, so we'll go with that. And we've got line segments OA, OB, and OC there. And to stick in line with the textbook, I've also done C as the middle point, even though that means they're not in order. So we're gonna reverse this. We're going to assume collinearity, have a look at some of the things that come out from that, and then reverse that or do the converse to show collinearity in the future. So here's my, here we go. Here's my space. So we're saying that AC equals M times AB. But first what I'm going to do is determine AC and AB and do some work with that. So AC, hopefully you can see, is equal to C minus A. So to get from A to C, there's no path there, but I can work negative A and then positive C. So AC is C minus A. And that means that C is equal to, so I'll turn it around, is equal to A plus AC. I've just done that, just a bit of a rearrangement there. But we also know something else about AC from our assumption up here. We know that AC is equal to MAB. So what I'm going to do is I'm going to change this now. That came out, whoop, that's mucking around with me, so I'll get a feeling this is about to crash. Can I just fix this? So I'm trying to be consistent. I've had a lot of people come and say, why don't you use the same things as the textbook does? Textbook starts with K in the parallel lines and then changes to M for this. I'm doing that. Okay, so you could use K is the point. C is equal to A plus AC. So it's equal to A plus M AB. That's from our definition above here. I've made that change, but we also know something about AB. So additionally, AB is equal to B minus, no, that's the wrong way. Oh, no, that's right. B minus A. You can see that. So again, to get from A to B, I get negative A and positive B. And so AB is equal to, so, that's right, that's what I want. And therefore, C is equal to A plus M B minus A. And if I expand that, because it's constant, that scalar, the distributive law works for this, so I can just multiply that scalar out. I get A plus MB minus MA, and that gives me 1 minus M times vector A plus M times vector B. And that leads, and I've sort of run myself out of the room a little bit, that leads to this statement. C equals lambda A plus, and again this is falling in line with the textbook, mu B, where lambda plus mu, like mu, was 1. Because obviously here we've got 1 minus M plus M, 1. So lambda and mu are kind of, they're complements like that. They add to give 1. And C is that point along there. So the point here is if I change that C, A and B back out to look at it a different way, that means that we want to show that OC is equal to what we call a linear combination of OA and OB such that this property holds. So if we can show that, then we have proven collinearity. So basically on the assumption of collinearity here, we've come down to this mathematical statement. Therefore, we can show this mathematical statement, then we've got collinearity there. And what does that mean? That means if you've got 3 points, and you can show that one of those points can be found by just doing some scalar multiple of the other 2 vectors, or one of those vectors can be found by the scalar multiple of the other 2 vectors, then you've shown collinearity. And it's still complex, but it's an easier property. Probably the biggest point here is that you'll get questions, which I'm going to do in example 1, where you might be asked to find a point that's collinear with A and B. And that's actually really trivial if you set up this statement and just choose gamma and choose mu, choose lambda and choose mu, such that this works. You'll have a point that's guaranteed to be collinear. So we'll do that in a second. Here's another little point here, which I wrote down to make sure I didn't forget it. If Mu and lambda are between 0 and 1. So they're still complements. It could be 0.6 and 0.4, but if they're between 0 and 1, then you get the situation where C is actually also a point between A and B. So what I'm saying here is if this is A and B, this holds if lambda and mu are between 0 and 1, but if lambda and mu aren't between 0 and 1, then C will be out here somewhere. They'll still be collinear, but the question might ask you to find a C that's between 2 points, to find a point that's collinear in between or outside, and it depends on the context as well. Does anybody have any questions on that? Last statement here before I go through a couple of examples. Collinearity is, and I'm sort of saying somewhat, if you have vectors drawn in 2D, it's usually pretty obvious and easy to find because you can represent vectors in 2D as Cartesian coordinates, and it's pretty easy to prove that they're collinear and they fall, you know, about linear functions. That's easy to do. You can find the gradient between each, etc. 3D, it's a bit harder. It's still possible, but 3D is a lot harder to visualize. So in 2D, you might fall back to more simple methods. In 3D, it's a little bit complex. So you've got to have these methods in place. When we get, at the moment I'm giving you everything you need for the PSMT. When we get past the PSMT and past the other two topics, we're going to come back to vectors, and collinearity will come back in a little bit more then. So we are going to build this into our linear function stuff. In particular, this idea here of OC being a linear combination of OA and OB, we'll talk more about. It's just this collinearity you do need for some of the stuff on geometric proofs, and the geometric proof stuff can be handy to you in your PSMT. So I want to give you that now. We'll come back to the collinearity as well. So here's one. How many examples have I got? I've just got one example. Given that OA equals that and OB equals this, they're three-dimensional vectors. Determine a vector OC such that A, B, and C are collinear. For your particular vector, determine the ratio between AB and AC. There's a connection here between that ratio and how you choose your lambda and mu. And as an extension, can you find an OC such that AB to AC is root 2 to 1? Is this possible? So we'll have a play around with that as well. But for now, I'm going to give you probably 3 minutes to have a play with that example before I go through and give you one answer. Remember, there's an infinite number of possible C values. So I'm going to give you one such answer, but I'd like you to have a play with it now. 3 minutes. Okay, so example 1, given OA and OB, determine vector OC such that A, B, and C are collinear. Dylan, can I ask, I did notice you made some choices for mu and lambda. What choices did you make? 0.5 and 0.5? Okay, so I won't do that one then. 0.5 and 0.5. I could make the trivial choices, 1 and 0, but obviously if I choose 1 or 0 in my setup from earlier, I will just get point A or B, and then I won't really have collinearity. So I can't choose 1 or 0 either. So what I might do, just to make it a little bit different, is I might choose 2 and -1 as my values. So remember our ratio from up here is that OC equals OA plus lambda OA, sorry, plus mu OB. So I'm going to have OC equals lambda OA plus mu OB, but I'm going to choose my lambda to be 2 and my mu to be -1, and I still follow that property of lambda plus mu equals 1. And so Dylan, if you can play yours out, that would be really helpful. We'll have 2 examples at least to do a comparison with. So in this case, I get 2 times 3i plus 2j minus k minus 1 times 5i minus j plus 3k, and that will be equal to 6i minus 5i plus 4j plus 1j, and then minus 2k minus 3k, which gives me a total of I plus 5j minus 5k. That will be my OC. Now, O is the origin, so it is setting up a coordinate system as well. I'm saying now that the coordinates, three-dimensional coordinates, 3, 2, negative 1, 5, negative 1, 3, and 1, 5, negative 5 are collinear based on our understanding. So we can create a collinear set of points just by substituting those values in. But if I draw my three-dimensional shape, or have a crack at it, that obviously can be quite hard to visualize. But if I try and draw this three-dimensionally, my choices, based on our information earlier, should give me a situation where C is not between A and B, but still I get collinearity. Whereas Dylan's, when he shows us his in a minute, should give us the other situation. So my points are, C is 1, which is there, 5, so I'm now out here, and then minus 5. So down here, 1, 5, minus 5, and there's a dotted line for that. My other 2 points are 3, 2, negative 1. So 3 is out here, 2 is there, and negative 1 is down 1. So I've got a point there. And then my third point is 5, negative 1, 3, sorry. Is it 3? 5, negative 1, 3, yep. 5's out here, negative 1's there, and then 3's up here. And I should have collinearity, but my sketch might not be perfect. But let's go say it's here. Oop. There. That's B, that's A, and this is C. So you can see my C has ended up outside of the AB line segment, but I should get collinearity from that decision. What were your coordinates for C? Plus half J, which is here, and then plus K, so up 1. Again, my diagram's not brilliant, but that should be about here, really. And you can see here that C's ended up in between B and A. But that's not a brilliant diagram. But that works. That's how we can find a third point that's collinear, or we can backtrack that to prove something collinear. For your particular vector, determine AB to AC. So I'm going to get Dylan to keep on working on this with his example. We're going to do it with our example. What do you suspect will be the case, just out of interest? Dylan's chosen a point such that mu and lambda are 0.5. What do you think his ratio will be? So, and this is, keep in mind, it's AB to AC. So AB to AC. So I see 1 to 1 will be this to this, maybe. So this will probably be 2 to 1. If you think that's 1 to 1, then that'll be 2 to 1. Whereas my one is AB to AC. AB is here, AC is there. That might be 1 to 1. That's what we suspect. Let's see what happens. It's always good to be thinking ahead a little bit with this. So first of all, to do this calculation, we need to know what AB is. And AB is equal to OB minus OA. So to get from A to B, you have to go from A to O, which is negative OA, and then O to B. I'm going to do that subtraction. OB minus OA is 2I minus 3J plus 4K. So this is equal to 2I minus 3J plus 4K. And that means that the modulus of AB is equal to the square root of 2 squared plus negative 3 squared plus 4 squared, which is 4 plus 9 is 13 plus 16 is 29, so the square root of 29. That's AB. And AC, which is the other part of the ratio, isn't it? Yep, AC is the other part, is equal to OC minus OA. So I've got my OC there, I've got my OA up there. OC minus OA will be 1 minus 3 is negative 2, 5 minus 2 is 3, negative 5 minus negative 1 is negative 4. So I get negative 2, negative 3, negative 4 equal to negative 2i, negative 3i, negative 4k, and that should be a j, so. And so therefore the modulus of AC is equal to negative 2 squared plus negative 3 squared plus negative 4 squared, square root, and that's equal to the square root of 29 as well. So we get the same thing. And therefore, that ratio, AB to AC, is equal to 1 to 1. It's kind of what we expected. Did you get a 2 to 1 ratio, Dylan? How close did you get? Root 6 to root 5. Yeah. 4.12, 2.5. So, and this is interesting because you've got to be careful about making an assumption based on, this is a simple case. We expected 1 to 1, we got 1 to 1. If there's any square roots or squares or cube roots or anything in play in these calculations, well then we might not get that 1 to 1 ratio. So we've got to be careful with that. We might not get a different ratio, but 1 to 1, the square root of 1 is just 1. So we'll still get the 1 to 1 ratio. So, can I do your calculation? And can you remind me what you said your coordinate was? I'm just going to write down over here in blue. Four I half J 1K. And my values here. So there's my OA and OB. So in terms of calculations here, I want to find AB to AC ratio. So my AB vector, first of all, is OB minus OA again. So I get the same AB vector. So that AB vector was 2I minus 3J plus 4K. And so there the modulus of AB was the same, square root of 29. And AC vector, in this case, 4 minus 3 is 1, so I get I. A half minus 2 is negative 1.5 J. And then 1 minus negative 1 is plus 2K. And so my AC is equal to the square root of 1 squared plus 1.5 squared is 3.25 plus 2 squared is 7.25. 7.25, or what's 7.25 as a fraction? 29 over 4. And so I could write this down as the square root of 29 over 2. And therefore my AC, sorry, let's change that. AB to AC ratio is equal to root 29 to root 29 over 2. And hopefully you can see that this is a 1.5 or 2 to 1 ratio. So we've got that 2 to 1 ratio, which is actually what we expected. That's not a proof, but it leads us to an understanding that the ratio will be dependent. And I've set this up based on an example or a question that they've used in a textbook example. But basically, if we change the ratio, and it depends on whether it's inside or outside, we get 1 to 1 here, and we would get something CB to CA would get 2 to 1 there. And it would actually match our lambda to mu. That's the interesting thing we get there. So keep that in mind as you're doing this. In the meantime, we're going to go on to geometric proofs soon, but I'll let you have a go at the exercise.